going to start with the first talk, and we're going to figure out the rest of the details as we go along. So please take it away. And thank you all for your patience.
Okay. How do I... Okay, sorry. Thank you for the introduction. My name is Daniela Lopes. I'll be presenting flow correlation attacks on Tor onion service sessions with sliding subset sum. This work was done with lots of people from universities of Universidade de Lisboa, Carnegie Mellon University, University of Waterloo, and Universidade do Porto. So, internet users face increasing surveillance and censorship, and this puts their privacy at risk. And also, journalists and whistleblowers need to share very sensitive information. However, there are several entities that may be powerful enough and may have motivations to try to find out who they are and who they are communicating with. Countries are, for instance, an example of entities that may have these resources. So this is where anonymity comes into play. So Tor is a system that is designed to provide internet users with anonymity, and for this it is a network composed of voluntary relays that provide anonymity. So to do this, how Tor works is it tunnels communications through three relays, a guard, a middle, and an exit relay. And this way, no single relay knows both the sender and the receiver of the communications. So this provides client-side anonymity. However, this does not protect the server, since the user still needs to know the service so that it is able to access it. So for this, Tor designed onion services, and the way this works is that the onion service will publish a set of introduction points on Tor directory servers, and when a user wishes to access the onion service, it will fetch one of those introduction points, establish a connection through it, choose a rendezvous point, and relay that to the onion service through the introduction point, so that the onion service can then establish a communication to that rendezvous point, and this way the client and the service are connected through a session composed of circuits of 6 relays. So this model already provides client and server-side anonymity, and this also allows servers to be less easily taken down or blocked, and users use many services such as DuckDuckGo to have these properties. So the problem here is that Tor has been recently subject to several attacks, and there is no real guarantee that Tor onion services are still provide anonymity. So we'll overview some attacks like website fingerprinting. This is the most commonly used for onion services, and this attack requires an adversary that can monitor communications between a client and their guard nodes, and then match those patterns collected against a set of known fingerprints from each website. However, this attack cannot find the service's IP, and so this way it cannot fully de-anonymize that service. So for that, we look into traffic correlation. Traffic correlation requires an attacker that has more coverage, that can put himself between more vantage points. And here, for instance, the attacker would need to be able to monitor the communications between the clients and their guard nodes and the onion services and their guard nodes. And then use those patterns collected to try to find matches, to find, for instance, that Alice was accessing x.onion. So this attack already allows us to de-anonymize both parties and find their IPs. However, existing attacks, or the state-of-the-art, are based on deep learning approaches that are targeted for Tor traffic to regular internet websites, not to Tor onion services. And from the experiments that we launched, we observed that it is not the most accurate for Tor onion services, and also it has some scalability problems. So, to fill this gap, we propose an attack based on this threat model. So here we have a set of clients and accessing onion services through the Tor network. And between each communication lies at least one internet service provider, or ISP. And we assume that multiple of these ISPs can collude together to monitor the traffic, extract features of that traffic, and then send it to a centralized entity, the correlator, that would then deploy one of the traffic correlation attacks. So in this case, the colluding ISPs are signaled by the little probe sign. And for instance, in this scenario, the correlator might be able to find Alice's and X.onion's IP, and the same for Charlie and Y.onion. However, Bob would remain protected because the ISP2 is not colluding. This might seem like a kind of unrealistic attack. The thing is that there are lots of ISPs that are actually very big, and they have a very big coverage over the Tor network. And also this scenario where we have multiple colluding ISPs is also not something new. We've seen this happen, for instance, in the Five Eyes Alliance, where multiple countries collude and agree to share this type of data on their users. So this is the main architecture for our solution. It is split into two phases, the filtering phase, which should be deployed by the probes in the ISPs, and the matching phase, which should be deployed by the centralized correlator. So the filtering phase is composed of two different stages, where the main purposes are to filter traffic as much as possible, so that we send as little traffic to the matching phase, and also to send already like the cleaned up and separated things that we need to pass to the matching phase to make its work easier. The filtering phase is also composed of two machine learning classifiers, whereas the matching phase is composed of a novel algorithm that we are presenting. And this also has a small offline training phase that is that its purpose is to tune the hyperparameters and train the filtering phase classifiers. So now into more detail, in the filtering phase, the probes will be collecting the traffic samples, and they will send the packets to a feature extractor that will extract features such as the burst bytes, packet sizes, packet times, and statistical features on these. And this set of features composes each flow. And then a set of flows is sent to the source separation. And its main purpose here is to distinguish between client-side flows and onion service-side flows. And then it sends the client-side flows to the target separation, which will separate the flows to ClearNet websites and flows to onion services. Then the separated flows would pass to the matching phase, which we'll see in more detail here. And it starts by pairing flows that were overlapped in time. Then counts the packets in each time unit, making buckets of the packets seen by each party. And then it passes it to the novel algorithm that I talked about. I won't have a lot of time to describe this here, but all of the details are in the paper. So this algorithm is based on a sliding window technique, and each sliding window is composed of multiple buckets containing the packet counts, and it slides through those buckets and to try to find matching volumes of packets observed at the client side and the total sent by the onion service. And for this, we leverage a dynamic programming approach to the sliding subset sum problem, and we optimized all of these by running this with the GPU support using OpenCL. So this way, all the windows are being done in parallel. Each of these windows will then output a similarity score, and the next stage will just perform a weighted average on those similarity scores, so that it can output a final correlation score for each group of flows, for each pair of flows. And this correlation score is the one that is going to decide whether the pair of flows is deemed as correlated or not. So to test this accurately, we developed a framework to generate data sets, and this kind of tries to mimic a small-scale Tor onion service ecosystem on top of the actual Tor network. And for this, we simulated several aspects, such as realistic geographical distribution of all the nodes, request concurrency from multiple clients to a single server, also simulating realistic client-side browsing behavior, and also hosting diverse real-world websites from actual onion services that we observed. And so we consider each unit to be correlated as a client session to an onion service. And here, for instance, we have an example of a client accessing a news website. Then he would browse through that website to find and click on one of those news. He would then browse through that news, spend a little time reading it, then scroll down to the footer and find more topics on other news. And this could be an example of one of the sessions generated by our framework. So now to the evaluation part of our system. We decided to present only the precision recall curves, since they account for dataset imbalance, and also because we can choose a custom threshold that will allow us to prioritize precision and minimize the number of false positives. So here we have the results for this first stage. We have almost perfect curve without average precision equals to 1. So this means that we can effectively distinguish client-side from server-side flows. For the second stage, the target separation, we obtain a slightly different curve, but still very good with average precision almost equal to 1, 2. So we can also effectively distinguish between flows to the internet and to onion services. And by the way, both of these classifiers were implemented using extreme gradient boosting. And now to the last phase of our pipeline. Here we see the zoomed-in precision recall curve for only over 90% precision, and we have multiple curves for different minimum durations for the sessions considered by our correlator. So for all the sessions, considering all the sessions, we obtain over 99.6% precision and recall. And if we restrict the minimum duration of the sessions for 6 minutes, we still we can actually obtain 100% precision. Now, considering this was the standalone results for this classifier, but also considering the imperfect filtering phase in the previous slide, we still achieve 99.5% precision. So we obtained very good results, but this would only be considerable a deployable attack if it can actually run very fast and process huge amounts of traffic in real time. So for the filtering phase, we need to perform a training phase, but we can do that in less than 6 seconds total, which would be very fast to retrain, which is also very important in this domain. And as for the inference time, the filtering takes less than 4 microseconds per flow, whereas the matching phase takes less than 6 microseconds per pair. Now comparing only the matching phase to the state-of-the-art, which is Deep Coffee, which is, I talked a little bit previously, it's a deep learning approach to focus on correlating only Tor traffic to the clear web. And this approach can correlate more than 1,000 pairs per second. However, our approach managed to correlate more than 100,000 pairs per second, making it 100 times faster than the state-of-the-art. So now we observe that we can deploy this actually to a large scale of traffic. However, is this still feasible by a realistic attacker? So we performed a study where we established several circuits between clients and onion services, and we observed the countries in which the guard nodes would be. And we calculated the de-anonymizing probability of de-anonymizing that circuit, which would be the probability of both guard nodes of a circuit being on the same country or set of colluding countries. And we found, for instance, that Germany alone has over 10% probability of doing this, which is a bit scary, and this is due to the guard node attribution being dangerously skewed in the Tor network. So to conclude, we observe that SUMo is effective and fast at de-anonymizing onion services, and also that existing entities can realistically deploy an attack like SUMo. So we focus and highlight on the importance of applying and improving existing countermeasures, such as using pluggable transports, which will change the patterns in the traffic, applying also concurrent multi-tab requests at the client side, and ensuring guard geographical diversity so that both guard nodes will not be on the same set of colluding countries. This is the QR code for the source code and datasets also. If you feel free to contact me on my email on the slide, and thank you for watching this presentation.
Very cool. Are there any questions? Raise your hand. I will walk up to you and state your name and affiliation. I will start with the first question while I walk over there, regarded to guard nodes. If we just massively scale up guard nodes, will this be sufficient, or do we really need to be more careful regarding the full geography?
You would need to be more careful about regarding the geography, because right now the probability of a guard node being on a certain country is very skewed. So there is a set of countries that have a very high probability of the guard nodes being there, and there is no real way right now of controlling whether both guard nodes will be on the same region. So we should ensure that not only we have more guard nodes, but the probability of the guard nodes being on the same country is very low.
And countries are bad because just countries, or is this more a consideration of ASNs?
We actually perform this study by country, by ISP, and by ASNs. We focus on the countries because it is a simpler analogy, and some of the situations even that we have heard on the previous presentations today, generally countries are an entity that may have a strong motivation and lots of resources for this. But we also perform the studies on ISPs, for instance, on the paper, if you want to see.
Cool, thank you.
Hi, thank you very much for your talk. I'm Ryan with Georgetown University in the Naval Research Lab. In your experiments where you were showing the results from the testbed, the correlation results, what fraction of Tor traffic did you assume the adversary had access to there? Did you assume they had full visibility or some subset of visibility?
Sorry, in which of the experiments? I don't think that I can go back like on the slides.
The precision for flow correlation was close to 1.
Yes.
In that data set, did the adversary have like a global view of Tor in that case, or just some subset?
In those results that I presented, they always assume full coverage, but we also have a section of the results on the paper that shows the results if we consider, for instance, flows coverage by continent or something like that. Of course, you can go more fine-grained than that, but that was the results that we presented on the paper.
Okay, great, thanks.
Any more questions? We have another minute or two. Actually 3. We started 6 minutes late.
So, hi, thanks for your talk. My name is Thorsten from University of Würzburg, and my question is, for your correlation here, how much traffic do you need if there's a small communication between the two parties? Can you already identify that, or do you need more traffic to be able to make this correlation?
More traffic in which sense?
So I'm not sure if this is correct, if I think about this correctly, but there might be one server communicating with another, and if there's just a small communication, like a few packets, then I'm not sure how you can correlate it, or do you consider like longer communication between the two parties, that there are more packages that you analyze?
Okay, so the more communications that are happening, like overlapping in time, the harder, in theory, it would be to launch an attack like this. However, the longer, as I showed like on the final results, the longer we can actually observe the communication, the easier it will get and the more accurate we can get.
Mm-hmm. Okay, and do you have a first idea how to counter your attack?
How to what? Sorry?
How to counter your attack, so prevent the attack from happening?
Yes. These countermeasures would work. The pluggable transports we tried at the time implementing OBFS, and we noticed that it would degrade the performance. The problem here is that it is still like we know that these technologies exist, but they are still not that used overall. But any of these techniques would already help deter our attack.
Thank you.
Cool. Any last question?
You say that you collected the data in a Tor network. So, University of Würzburg, the same as Thorsten sitting beside me. So my question is, did you communicate with the Tor board about collecting data? What did they say?
The data that we collected is data generated by our automated clients. So we never use real user traffic to evaluate this attack. We did use the Tor network in the terms that our communications would go through the actual Tor network without using simulators or any of those approaches. But we did communicate this attack and some of the initial results to the Tor project. The underlying algorithms that we are applying have changed so far a bit. However, the overall architecture and the implications and countermeasures that should be applied remain the same. Yeah.
Cool.
Thank you all.
Let's thank Daniela again for her talk.